Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Thanks everybody for coming out. It's my pleasure to introduce Andreas Zeller, who's been here visiting us for the past week or so. Andreas came out for 2 months in March, is that right? Earlier this year. And this is the paper that he's going to be presenting is one of the pieces of work that he worked on with us, with Tom Zimmerman and myself. Back in Germany, Andreas is a full professor at the University of Saarland. Has done work in a lot of areas of software engineering, has written a book and a number of papers, and most recently, I think it was just in June, he was inducted as an ACM Fellow. So we're happy to have him here. And we look forward to your feedback. He's actually going to be presenting this at Promise, which is the international workshop on, or excuse me, conference now on predictive models in software engineering. So, Andreas.
Thank you very much. I see you can all hear me. Marcus, can you hear me in the back there? Yes. Wonderful. Great. Okay, so this is failure is a four-letter word. And as the title already says, this talk is about software failures. Software failures, as you all know them. This is one of the more spectacular examples now in full video. This is the crash of the Ariane 5 rocket. One of the many, many software failures we have to deal with in real life. And besides programming, probably one of the major obsession of computer researchers. How can we find all the bugs and how can we eradicate them? One particular interesting line of research in here has been the analysis of software histories. What you see here is actually all the classes of Firefox. Actually, we have this is an anti-tree map where you can also see the individual packages. And in this picture, what you see here is we have color-coded the defect density in the individual classes of Firefox. What you see here below, for instance, is classes in the JavaScript engine of Firefox, and you can see these red boxes down here are in classes where a high number of security bugs showed up. There's also other places in here. Here's the layout base, for instance. This is where cross-scripting attacks happen. Over here we have the document object model, where also a number of attacks have happened, and where such bugs have been fixed in the past. Such results are the results of a pretty new field of software engineering, which is mining software repositories, where you go along and where you look at the history, in particular change and bug history of systems, and then you map them to individual places in your source code in order to figure out where the most bugs have occurred in the past and where the most bugs have been fixed in the past. This field has taken off enormously since 2004, I think that's when the first workshop in the topic happened. At this point, there were about 20 people attending. Now it's almost a major conference with 150, 160 people attending, and plenty of people all along the way who work on this kind of research. The interesting thing is, once you see a picture like this, is you wonder how can it actually be that there's specific places in your code where there's many bugs, or many bugs of a specific kind, and how can it be that there's other places which are literally stable from the beginning? So what people typically do is you go and associate this with appropriate failure causes. Failure causes such as, for instance, the quality of your developers. You look at appropriate features of your developers, and you try to correlate them with specific features of the code they've been writing. One of the things that my student Tom Zimmerman and myself at the point found out, for instance, was that in Eclipse, the more experienced you were, the more bugs you would create, very much in contrast to what this picture shows over here. We can also go and try to correlate failure causes with specific management styles or with specific ways the team works together. You can, for instance, go and try to figure out this is something that actually was found out here at Microsoft Research, that if you have many people from different teams, and none of these individuals actually takes responsibility in the actual outcome, turns out that the resulting modules have a higher failure rate than modules for which there's individuals who take responsibility. This is another interesting point that researchers have been investigating. And then, of course, there's the issue of complexity, all sorts of code features which people have looked upon, various metrics that you can go and correlate with these failure data. Obviously, a high complexity, you would assume a high complexity yields more bugs. Certainly, if the complexity is high, it dominates everything else. The problem with this is that at this point, what we see is actually a large number of studies all trying to correlate failure cost with various aspects of the code and its process. Which means that for a manager, the situation is actually pretty much confusing because there's so many relationships between failures and features of code and process, such that something occurs what we call the cost of consequence. We may choose to work on a specific thing. We may work, say, for instance, on a management style. We may work on reducing the code complexity. We may work on increasing the abilities of our developers. But all of these have costs, and all of these issues have costs. And there's the risk involved with that all of these actions that we could possibly undertake will actually not change things. And we see this problem primarily as a problem of, well, it's a problem of too many results. It's too many results, too many findings, and it's hard to choose the right one between them. It's hard to choose the right one of all of these. What I'm going to suggest in this talk is that we go back to the very basics. Back to the very basics of programming. What does programming in its true sense actually mean? And in its true sense, what is programming from the beginning? Programming in the beginning is simply, well, we're typing. We're typing our code on the keyboard, and we're producing code. This is what programmers do at the very lowest level of abstraction. I'm going to make this a metaphor. I'm going to say, actually, we try to avoid all abstraction, trying to come up with abstract concepts of the code or abstract concept of the process, but rather we're going to look onto the code as it is right here in front of us, simply as a combination of individual characters as they form up the source code in the very end. And this is precisely the level at which we analyze code, simply by looking into its individual constituents, which means individual characters. Actually, this is if you apply such a thing, if you simply look at the distribution of characters in Eclipse, you already find that there actually is a certain bias in here because individual characters are not equally distributed. For one thing, there's plenty of printable characters in code, and there's very few non-printable characters except for space and for newline line feed actually, which make up the gist. And there's plenty of lowercase letters in here, very few uppercase letters in here. And this difference in distribution, you can also see E is the most prominent character in the lowercase letters. This difference in distribution actually points to the concept. We may actually be able to look at this distribution of individual characters in source in order to come up with empirical findings on them. So what we looked at is, we looked at the publicly available Eclipse bug dataset. This is available for download for anyone, and plenty of people actually have worked on this. It comes in 3 releases, from 2.0 to 3.0, and it consists of between 6,000 in the early releases, 10,000 files in later releases, each files with individual defect rate, which means that the number of defects which have been fixed in the appropriate file over time. Here's a few more features. This is the number of characters that you find. We have 45 million characters in Eclipse 2.0 and 76 million characters in Eclipse 3.0. This is something we look at. And this is the number of files that actually have defects. This is about 1/6 of all files in these settings have had defects fixed in the past. So we're looking at 3 hypotheses here. The first hypothesis is we can actually use these programmer actions, these very basic typing actions, to predict defects in Eclipse or and elsewhere. The second is we can go and find out which programmer actions actually are the ones that are mostly correlated with failures. And third is we can actually go and prevent defects by restricting such actions. And let's start with the first one, predicting defects from programmer actions. So this was a fairly straightforward approach. We simply trained a machine learner, simply trained a regression model on the number of on the distribution of characters in each file, and used the number of specific characters in each file to train it, and we used this to make predictions on whether a specific file would be failure prone or not. This is our results for Eclipse. We used as training sets, we used Eclipse 2.0 to 3.0, and we checked this for the very same sets, Eclipse 2.0 to 3.0, so you can see, for instance, if we train a regression model in Eclipse 2.0, and we use this to predict which files would be defect prone. In later releases, Eclipse 2.1 and Eclipse 3.0, we find that we're actually able to come back with about 50% precision, meaning that every second of our predictions regarding defect prone files is actually right. Eclipse 2.1 is even better. Eclipse 3.0 is still better. Interestingly enough, and this is very important for our work, is if we use the same set for training and prediction, that is, we learn things in Eclipse 2.0 and we predict things in Eclipse 2.0, this is actually where we get the highest numbers in terms of precision. And this is very important because normally you do not want to learn from some earlier version to do things in your current version, but actually you'd like to learn things from your current version because this is the version you're currently working with. And if you're learning from this current version and applying it right away, that's when this whole approach will be most effective, of course. In terms of recall is not as good as precision. We're about, on average, this is about 20% recall, so we are able to identify correctly 20% of the defect-prone files. But this is on par with same bug, generally with bug detecting tools. If you use an arbitrary, say, a static bug detector and apply it, you'll find a number of bugs, but you'll never find all of the bugs. There's always a number that will be. We will have a number of questions at the very end if you'd like to have it, okay? So that's the first thing. So by training a regression model on the distribution of characters and the number of characters in files, we can very easily predict defects in various Eclipse versions. Let's come to the next topic. Can we actually figure out which are the programmer actions that are most defect prone? And this is where the truly interesting stuff begins, because we actually looked at the correlations of the individual characters in files and looked at whether these individual characters would correlate, or what their correlation coefficient with defect proneness would be. So here you see the correlation coefficient, and here you see the correlation values for the individual characters, and you can clearly see here that there's 4 values that stand out. This is the lowercase letter I, this is the lowercase letter R, this is O, and this is P. These are the 4 characters in our data set which had the strongest correlation with failures. And we found that so striking, not only because, well, these 4 clearly stood out, but also because these 4 letters actually make a nice acronym. We call this the IROP principle. Oh, I'll come to that in a second. You have the IROP principle, which incidentally is also airline slang for irregular operations. So this makes a nice meme to remember. Simply remember IROP, and you'll find the 4 important characters that correlate with failure. This was striking for us because now we knew which programmer actions led to failures, and so we had a clear sign what actually were the basic actions we had in the end. The third point is, can we actually go and prevent defects like this? Can we go and, I'll come to this in a second, Mike, I'll be there at the end. The third thing is, can we prevent defects by restricting program actions? And what we did here is, we first went and mapped the individual characters on keyboards. So we came up with this concept of color coding, of color coding the individual correlations of the individual characters on a keyboard. So we found if numbers, for instance, are pretty okay. But here again, you see the 4 letters of failure in here. Enter actually also was one of the non-printing letters that correlated with failures. And So we thought that by color encoding this, we would be able to provide immediate feedback for programmers, such that they would be able to see exactly the consequence of typing that key, of introducing that particular letter into their code. So we thought, well, that's one thing, but didn't respond too well. So we went for a more drastic action. So we set up a special keyboard, which is shown here. And this keyboard actually eliminates the possibility. Well, you can still press Alt and something, but this is really difficult. So we simply eliminate these letters up here. So making the cost of these letters immediately clear. You'll find that there still is an Enter key. That's right. This is right. Formally speaking, we also should have eliminated an Enter key in here. But the thing is that if you eliminate the Enter key, what happens is you get many, many more defects per line than beforehand. So we kept the Enter key in the keyboard. But we eliminated the other letters. So this is what we thought then would eventually lead to better code. However, it turned out we had to introduce a number of new coding standards because, of course, your regular code, as you have it in here, has a number of these IROP characters in there, and not only that, also the keywords in here have IROP letters in here. So we had to rename them appropriately, which actually is fairly straightforward. Instead of if, it's when, integer becomes num, and return becomes handback, which is essentially just the same. Which is actually, we avoid these 4 letters of failure. And the interesting thing here, this is 100% semantics preserving. So there's no chance of this automatic translation introducing any new bugs in here. So everything stays as before, except that now we can avoid the correlations between these 4 letters and failures. And these keyboards actually very nicely stuck on with our test persons. So what we found is that they also use these keyboards in real life for their daily communication. And this is what one of them wrote us on his keyboard. We can shun these set majuscules and the text stays just as well as incidentally. Let us just ban them. You'll see there's no IROP anywhere in this text anymore, and this has become a true habit of developers. So this is for our third hypothesis. We can prevent defects by restricting programmer actions. And this is true just as well. Now I understand you have a number of questions. Let me illustrate them. Since the paper has been published on the internet beforehand, I've received a number of questions and I'd like to address them all. The first thing is, of course, is this externally valid? The question here always is, you only analyze a small set of actual instances. Is this actually true for all instances? And I can easily shun this off simply because we have been looking at no less than 177 million individual characters. This is something which actually brings our statistical package, which almost makes it crash because it's so huge. This is one of the largest studies ever in terms of numbers. So thousands of characters, thousands of defects, 170 million characters. Really, this is huge. This is something which really encompasses a large body of code. Next question is about internal validity. Are the correlations that we found, are they significant? Are they statistically significant? And all of them are. All of them are statistically significant. We put them to the test. All of them are as they are. And the last question, of course, is this in terms of construct validity? Construct validity means are the constructs that we build, are they actually appropriate? And the good news about this work is there is no construct. There is no abstraction such as making a model of the process or making a model of the program or anything. We just look at the basic stuff, the characters that are in there. And there is no construct, no abstraction from our part that could possibly have interfered with that. So after these facts, let us focus a bit on future work. First thing, we already saw an instance of that is automatic renamings. What we're currently working on is we're setting up automatic renaming programs that go and take source code as well as other code and simply rename it appropriately. If we find an appropriate semantic replacement, such as promise, we can rename this to engagement. Other words for which there's no good substitution, or simply eliminate the appropriate letters. We're also thinking about what could actually be the reason behind all this. And what we found is, and this is striking, is that there's a number of words that do have negative connotations, such as a failure, mistake, error, problem, bug report, that all contain these 4 letters of failure. In contrast, say, to positive words like success or fame, which we all want, of course. And it may well be that while typing these letters, there's sort of resonance that goes on, an internal resonance towards the risk of making a mistake. This is what we think, and thereby focusing on words without the 4 letters of failure, I think we can get a more positive attitude, and this more positive attitude will also then come up with more positive test results. And of course, we are generalizing. The interesting question is, so far for us, is this true just for Java code as we looked at it? Does it also work for C++ code, or is this actually something that would work only on English-speaking code? So right now we are looking at a big base of Russian source code, Russian-speaking source code, and what we found already is that for this Russian code, which is very different from the source code we've seen so far, just as well strong correlations between individual letters and between the abundance of individual letters and the number of defects in a file. So I think we are looking out to something that really works across a large number of domains. So this was failure is a 4-letter word, and with that, let me get out of this again and now give you a few hints. Obviously, you found this out. There are very few serious things in that. And now let me point out why we did this whole thing, why we wrote this paper in this very way. It's a fun read. That's at least what I hear from many people. And let me give you a few explanations on why we did this and what we did in here. So the first thing is what we came up with in this research is, well, we came up with plenty of correlations. That's right. And the true thing is, you can, in any big data set, you could always find lots of correlations if the data set simply is big enough. There's a couple of famous correlations. Say, in Germany, for instance, where I come from, you can find a very clear correlation between the abundance of stork and between the decline of the number of storks and the decline of the birth rate. It's correlated almost to the point. The fewer storks, the lower the birth rate, for instance. Sure, there's always a correlation. The thing is, for storks and babies, there's at least a couple of theories that explain the whole thing, no matter how bogus they may be. However, over here, there's no such theory at all, and I'm simply making this up that there could be something. The second observation is machine learning works. You can train a machine learner on a number of features, and it will make accurate predictions based on these very features. It doesn't matter much which features you feed in there, which is one of the reasons that this particular prediction works well. And this prediction actually is, there's a number, the fact that we use the same set as a training set, as the evaluation set, of course, is an absolute no-no. I hope some of you have remarked this during the way. So this is the reason why this particular line in here has particularly high values. Cherry picking is another problem that we actually sometimes see in published scientific papers, where people come along and say, we have invented this nice technique, and now let us evaluate it. We selected 5 programs on which to evaluate it. Period. No discussion on how these 5 programs were chosen or anything. They're just out there. Okay. So in here, and I think one of you pointed this out, here's the n, which actually has a higher value. That's right. But we decided to go for the other 4 characters because it made this nice acronym. If we had gone for n, it would have been PORN. This would have become the porn principle, which probably would have lowered its acceptance rate. Although it could have been fun coming up with the porn principle in empirical software engineering. And other minor things is, look at the scale, for instance. If you look at the scale, you see that any difference in here are hugely exaggerated. If you look at the true distribution, the true correlations on a regular scale, say from 0 to 1, you'll find this is just a flat line. And actually the flat line goes over all characters, okay? Because obviously, the more characters you have in a file, the higher the chance of having a bug in it. It doesn't take lots of rocket science in order to come up with a conclusion like this. Yet again, this paper is published on this very fact. The larger the file, the more bugs. You look and behold, which is maybe mildly interesting the first time, but it goes on like but there's actually people who published a whole series of papers on that. It's very, very much remarkable. Next thing, of course, fix causes, not symptoms. You need to find out what's the actual cause behind something. Just going for the characters doesn't work. A word like 100% semantics preserving simply means that whatever you do has no impact at all on the other side. And finally, actionable findings. You need to have findings that actually will not only, say, be of interest to the reader, but actually will impact the way people work, and also show up with some credible evidence that the findings you have will have some impact. I'd like to point out also that this research was inspired by a comic called XKCD. A very nice comic, by the way. I'm happy to endorse it over here. So this is Jelly Beans cause. This is the significant comic. Jelly Beans cause acne. Scientists investigate. Oops, no correlation between any kind of jelly beans and acne. Okay, so if there's no correlation between jelly beans and acne, maybe there's a certain color that causes it. So you go and investigate it. You do this first for purple jelly beans, brown jelly beans, pink jelly beans, blue jelly beans. You never find a correlation. But it turns out that if you do this 20 times with a confidence factor of 95%, then you will actually find at least one color where there is such a correlation. Or we say over here, we found a link between green jelly beans and acne. Whoop! This is a very interesting result. And the result of these 20 experiments is, of course, you focus just on the one result that strikes out with this high error rate, and then you come up with the result that green jelly beans link to acne. Wow! Look and behold, 95% confidence, which is actually all true. But and this is of course also a problem because, for instance, all the negative results we produce, and which never ever get published, eventually cause a bias in public perception, and this is exactly what comes out at the very end. So for us, we should go and educate reviewers, we should go and educate professionals, we should go and educate future generations of computer scientists to know more about empirical evidence, and also to know about the many ways one can fake empirical evidence, not so much to use these techniques, but to discover them. And of course, there's also a nice paper on this, which actually has all of these results, a parody in empirical research, which on the first 4 pages actually comes as a full-blown description of what we claim to have done, and then there's 2 pages of revelation. And feel free, if you do a class on empirical research, to pass on the first 4 pages to a student. Maybe you can eliminate this parody in here and have them figure out all the many ways that this research may be wrong. This is where we have the paper, the word source, the word original paper, as well as R scripts and the data available. The slides here are available on that site as well. And with this, I'd like to conclude my talk on failure is a 4-letter word, and I'm happy to take questions. Thank you very much. Yep.
Can I ask a question in character?
Yes, please. Go ahead.
So, given your results, and you showed the keyboard slide, and the numbers were low, they had low correlation, right? So what if we just use the number pad and type in octal, right? Because the number pad is entered, and it has the numbers. So if we just type in the numbers as code, won't we get a lower defect correlation?
This may well be. This is actually typing the numbers in octal, simply pressing Alt and pressing the numbers in octal, actually was perceived as a workaround by our interns in order to enter these characters nonetheless. But it was clear to them that they were this way it became explicit to them that they were just entering some dangerous ground. Okay, and this made them more aware of what they were doing right now. So so what we actually found was that code with these letters entered after we had distributed these keyboards tended to be of better quality because people were more aware and people tended to focus specifically on the risks as well.
Thank you.
So what would be your estimate that what fraction of all the research in this area, in empirical software engineering, actually would meet your standards for being statistically reasonable?
So there's sayings that 80% of all research anywhere, not only in empirical research, in empirical software research, but 80% of all research is empirically flawed. This is a number that goes along. If you're
Do they provide evidence?
there's estimates to that, so a simple example. If you look at, say, if you look at headlines, for instance, in the newspaper for whatever A is related to B, whatever, and you actually look at the real papers, you find out that this typically these are studies that are being bought by specific companies where the people who actually respond to them are carefully selected, and where it doesn't take rocket science to figure out that this is flawed from the beginning. But yeah. Exactly.
Research and so on, and people do retrospective studies.
So for empirical research, I can't come up with a true estimate on that. What I see is the papers that I'm supposed to review as a reviewer, and I can see that about 1/3 of the papers I get to review have very serious empirical problems. However, these are not the papers that eventually get accepted. That's the good news.
Good to know. I'm really.
Your comment about how people tend to cherry pick a few examples and say we have this technique and it works well in these examples,
yeah.
That strikes home with me in a bad way, because some of my research into program verification, I might come up with a technique that there's a well-identifiable hole in some particular verification method. I come up with a technique that fills that hole, but I don't ever claim that my technique is like a one-size-fits-all verification method. Yes. So I find some programs that do where it demonstrates a benefit, and I present results for those programs. I'm not making any statistical claim that this technique is good or bad, but the trouble is I always have this nagging feeling that if you took my technique and ran it on an arbitrary program, it almost certainly wouldn't give you any results, right? It would just say it couldn't verify the program. If you combined it appropriately with the right other techniques, it probably would work, but only if you knew magically which techniques to use. So it seems like it's something I feel a bit guilty about as a researcher, but I don't see a way around, because I don't think my techniques are rubbish. I think they're useful. Can you give me some advice as to?
Yeah, the thing is simply whether your research or whether your contribution by construction will always do things better if it works. So if you can come up with techniques that by construction are set up in a way either it improves things or it keeps things as they are. Okay, then there's no risk whatever involved with them.
What if you say, okay, run the two things in parallel?
But there's also techniques which you think may make things better, but which also run the risk of making things worse. Bug finding is a typical example of that, because with most static bug finding tools, you have a number of false positives, and you need to offset the number of true positives, that is the value of the bugs you find, versus the cost of the many false positives that such tools produce. Having been at Google just a couple of weeks ago, they said in my face, for us, it's much better not to have false alarms at all. For us, it's most important not to have any false positives, because they get distracted by these false positives. They think that this devaluates the tool, and so for any recommendation, say empirical study can get you. For any such recommendation, there's always the risk of such recommendations going in the wrong direction. So in these situations, you clearly have to evaluate, well, what's the potential benefit, but also what's the risk, and then if there's risks involved, one would like to see how large the risk is, how large the benefit is, and this, of course, can best be done by applying the technique on a number of representative subjects.
All right. Let's thank the speaker one more time.
Thank you.
Thank you for coming out.